Hey everyone, my name is Chetan Bansal. I'm a research engineer at Micro Research. I'm going to present DeCaf, which is a framework we have built for diagnosing and triaging performance issues in large-scale cloud services. This is joint work with my colleagues at Microsoft. So, before we go into the details of Project DeCaf, let's briefly talk about the motivation and the background. At Microsoft, and even in other cloud companies, we build and operate hundreds of large scale cloud services. All of these services have KPIs or key performance indicators, which are tied to customer revenue and satisfaction. Some of the performance indicators which are tracked and measured are service latency, availability, error rate, etc. Root causing of regressions in these KPIs is generally very time-consuming, laborious, and requires deep domain knowledge of the service and the environment. Some of the key challenges which you observed while working on performance regressions are: first, these services often generate large amount of logs and telemetry, up to terabytes per day. This makes any manual analysis or root causing near impossible. Second, the logs and telemetry generated often contain mixed type of attributes, both categorical and continuous. Continuous attributes such as performance counters, subcomponent latencies are very common. Even categorical attributes such as build version, operating system, browser, data center are commonly logged. This prevents us from using prior work in this area, which is heavily focused on trend analysis or anomaly detection. Lastly, high cardinality and dimensionality of the logs also introduce challenges which prevents us from using brute force techniques for diagnosing performance regressions. Let's briefly discuss some of the practical constraints with respect to diagnosis of performance regressions. First, engineering teams have limited resources, so they can only investigate and root cause regressions which impact the metrics at a macro level. Second, due to high cardinality, there are millions of users or cohorts, and it's not possible to investigate and analyze each individual cohort separately. Third, multivariate regressions or regressions which are with a narrow scope of impact can be really hard to diagnose and root cause. For example, there can be regressions which impact only a particular data center or a particular build in a particular region. Lastly, we want to detect and diagnose regressions before they become customer escalations. To solve these problems and challenges associated with performance regressions, we have built and deployed DeCaf framework for several services across Microsoft. As a first step, we aggregate and collect logs and telemetry from different data centers to which these services are deployed. Next, we do feature selection and data sampling, where the feature selection is primarily to prune the high cardinality attributes such as correlation IDs, which are not useful for diagnosing performance regressions. We also do data sampling if needed based on the computational constraints and runtime requirements. Then the key step of the DCAF algorithm is the random forest ML model training, where unlike conventional machine learning, we don't use the trained model for predictions, but we analyze the trained model to extract patterns which are correlated with regressions. Once the model has been trained, we analyze the model, rank these patterns, deduplicate them, and upload it to a central SQL database from which we do trend analysis and send out reports and alerts to the end engineering team owners. Now, let's talk about the performance regression localization. For that, First, we train the random forest ML model to predict the KPI such as availability or latency, which is being root caused. Next, we analyze the trained model and extract patterns or correlations, which can help localize the regressions. This is an example issue which was diagnosed using DeCaf. It first highlights the patterns, which is a set of predicates, to help localize the issue to a narrow population or cohort of users. It also provides metrics such as impact and how many requests were impacted, which can help prioritize different regressions. We chose random forest models because of several reasons. First, and most importantly, they're highly interpretable. Second, since a random forest model is composed of a multitude of decision trees, they can be parallelized and scaled. Third, unlike some of the machine learning models, random forest models can support both categorical and continuous features and also target labels. As a last step, we trace the patterns which are mined by DCAF into various categories. For this, we store the historical data in a SQL database, and whenever we generate any results, we compare the current results with the past historical results. Subsequently, we do pattern mining and categorize the current results into new, regressed, or top issue categories. This helps the on-call engineer prioritize and focus on the issues which they're interested in. This is done based on a moving 14-day window of results, and then we leverage the standard deviation and the average metrics, statistics to categorize into these categories. To conclude, we have presented DeCaf, which is an ML-based framework for localization and triaging of performance regressions. At Microsoft, it has been used to diagnose and discover several issues across multiple services and client applications. It has also significantly reduced the manual effort which goes into investigations of these performance regressions. Thank you.